Okay, let's continue now. We are going to talk about valence electrons and ionic radius today. So, kicking it off, valence electrons are the electrons found only on the outer energy level of the atom. Okay, they're only on the outer energy level. So, if you look here, if we were talking about element, let's see, 12, magnesium, we're only talking about the electrons found in the last energy level, this third energy level for magnesium. Okay, so everything in the first and second energy level we're not thinking about, just the last two. So the A groups tell you the number of valence electrons, the A groups. So 1A means 1 valence electron, 2A means 2, 3A, 3, 4, 5, 6, 7, and 8. You might ask, why aren't we considering the B's? Well, we're not considering the B's because only the electrons in the A groups, okay, in the S and the P orbital groups, are going to be very useful, I'll say, in helping us figure out bonding. That's due in large part due to the fact that the valence electrons are very, very important for covalent bonds, which we'll talk about in the next unit. But for the time being, you just have to understand how to find the valence electrons. So, along with this idea, we have to be aware that when metals give away their outer electrons, they have a full valence shell in the row above them. So if we were talking about sodium, sodium here could be shown as the positive center, the protons and neutrons, 11 protons, 12 neutrons here in the center, and then I've got 2 electrons in the first energy level, and then I've got 1, 2, 3, 4, 5, 6, 7, 8 in the next energy level. And if I'm sodium, I have 1 lone electron in this third energy level. Well, if I'm sodium, I would much prefer to get rid of that one, and then I end up looking here just like neon. Neon has a total of 10 electrons, like we see here. So if sodium, Na, with its single electron, gives that one away, it ends up looking like neon. Okay, and that is the Na plus ion. Na plus ion has the same valence shell as neon. So metals give away their outer electrons, they end up looking like the noble gas in the row above them. So another thing that we see here is we get an imbalance of charge. Okay, so we'll have an imbalance of charge, and this happens because our sodium, before, remember, we had 11 protons, we had 11 electrons. Now I have the same number of protons, but I lost one of my electrons, so now I only have 10 electrons, which means I have a positive charge. It's a +1 charge. So I have an imbalance of charge based on that. The repulsions that I have, if you recall, I've got repulsions happening between here and here, and I have repulsions happening between here and here, right? And that is expanding the radius. So I have fewer repulsions. I have that imbalance of charge, which means I have more pull inwards, and so this makes the ionic radius smaller. So this is a look at what actually happens with sodium. Again, the atom, it is 186 picometers from the center out to the outside shell, and that gets reduced to 95 picometers in the ion form. Now a similar thing happens with nonmetals. Nonmetals are going to they will receive more outer electrons, and that way they can get a full valence shell in the same row. So if I'm thinking of chlorine, for instance, recall chlorine, it has that filled first shell. The second shell is filled, which we see here. But the last shell, you notice this is going to be in group 7A. If it's in group 7A, what that indicates for us is it has 7 electrons on the outside shell. So I only have 1, 2, 3, 4, 5, 6, and 7 electrons there. So my issue is I need a full valence shell. What chlorine can do to fill that shell is it can take an electron. So here, chlorine as an atom is going to take an extra electron. We'll show that there. That allows it to have a filled shell. So the chlorine takes an electron and then looks like argon, and that will be the chlorine minus the Cl1 minus ion. So this will again cause an imbalance of charge. This time around the imbalance is the opposite though. For chlorine I have 17 protons and I have 17 electrons in the atom chlorine. But in the ion I still have my 17 protons. However, I've gained an extra electron, so I have 18 electrons, and that gives it a -1 charge overall, which is why we showed as a Cl with a superscript of minus. So what happens there is now I have an extra electron, which means I have even more repulsions. I also have an imbalance of charge. I have more charge, more negative charge, than this positive center can hold on to as tightly. So it has to kind of ease up the grip, if you will. It has to loosen its hold on its existing electrons so that the new electrons have a space to be where their repulsions can be minimized. So this in turn makes the ionic radius larger. When we see that happening, chlorine begins at 100 picometers. When it gains that extra electron, it goes up to 181 picometers. So hopefully that made some sense for you. Let's work out some practice problems. I'll give you a second to pause this. That was your second. Now let's move on. So how many valence electrons are found in each of the following atoms? Potassium. Potassium is in group 1A, so it has 1 valence electron. Aluminum. Aluminum is in group 3A, so it has 3 valence electrons. Sulfur is in group 6A, so 6 valence electrons. Nitrogen is going to be found in group 5A, so nitrogen is going to have only 5 valence electrons. And lastly, xenon is a noble gas. That is in group 8A, so it has 8. Which of the following have exactly 4 valence electrons? So if you look at iron, you see that's a transition metal. So we don't even consider the valence electrons of transition metals. Oxygen has 6, so that doesn't work. Fluorine is in group 7A. Cross that one out. Carbon, hey, we have a winner. That one is group 4A, so that one works. Selenium. Selenium is found below oxygen. They're in group 6A, so 6 valence electrons. That doesn't work. And lastly, silicon is again in group 4. Silicon falls right below carbon. So carbon and silicon have exactly 4 valence electrons. So what happens to the size of a potassium atom when it forms a positive ion? Okay, so there are a couple of keys in this question. We want to know what happens to the size of potassium when it forms a positive ion. To form a positive ion, it had to give away, right? It had to lose a negative electron. If it lost an electron, it has that imbalance, that positive imbalance. Okay. If it has that positive imbalance, also you can consider this because it is a metal. To form a positive ion, it's a metal, right? A metal, it lost electrons. This imbalance is going to reduce the size, okay? It will reduce the size of the atom when it becomes a K+ ion. Okay, so one thing to be aware of is, again, anytime they lose electrons, anytime we're talking about a metal, when they form an ion, they're going to get smaller. Okay, they will reduce in size, they get smaller. Question, will nitrogen get bigger or smaller when it gains electrons to become a negative ion? So the first thing to think here is nitrogen. Nitrogen is a non-metal. That's the key. Non-metals will take electrons, right? So that means that they're going to end up being negative ions. That's the other key here. A negative ion, anion. So if we're forming a negative ion, it is going to gain electrons, which means I have more repulsions, more repulsions means these electrons aren't going to be held as tightly by the positive center, so they will get bigger. Okay, predict the radius changes to each of the following. Okay, so as a basis of this one, I'm just going to consider metal, nonmetal, okay, and valence electrons. So aluminum, metal, means that its radius is going to get smaller. Copper, metal, gets smaller. Sulfur, nonmetal, gets bigger. Pb is lead, so that's a metal, gets smaller. Phosphorus, nonmetal, gets bigger. Magnesium is a metal, it gets smaller. Iodine, nonmetal, gets larger. And helium, while it's a nonmetal, it is a noble gas. And noble gases do not form ions. Okay, kind of a trick on that one. Hoping you would catch it. So, noble gases do not form ions.